Um, Here we go. Good. So last time we left off talking about testing goodness of fit by means of the chi-square tests and the multinomial distribution. Now, you recall if we have a categorical distribution, or variable, which can have a value from certain number of categories, which can represent subintervals from a real line if we are discretizing a distribution, then we can count the numbers of the actual cases in which random sample values fall into the individual categories n1 up to nk model using this multinomial distribution, and we can compare the observed counts in the individual categories with the expected counts in the individual categories and apply the chi-square statistics. So just to recall, let's think, let n1 up to nk represent the observed number of cases in each category. P1 up to pk probabilities of the categories, and n times p1 up to n times pk are the expected number of cases in each category. Then the chi-square statistic, which is sum over all categories, I goes from 1 to k, ni minus n times pi squared divided by n times pi, has the chi-square distribution with k minus 1 degrees of freedom. Now, this helps us for testing hypotheses when we assume that the counts follow some distribution with probabilities p with a prime, and we are testing the hypothesis whether the probabilities are actually equal to some given values against the alternative that we do not. And if we compute the expected number of cases in each of the category under the null hypothesis, and we would find out that this statistic is too large, meaning that it is larger than the corresponding chi-square critical value at probability alpha, then we reject this null hypothesis on level of significance alpha. Last time we have seen a simple exercise when we were just having a dichotomic variable boys and girls, and we were testing whether the probability that a kid is a boy and girl are equal. Then we have seen that we can apply this approach when we want to test whether some distribution is equal to some given family. When we, for example, want to test whether the data come from normal distribution, what do? Is we can slice the real line into subintervals and then compare the expected and actually observed counts in the individual intervals. Now, when we are slicing the interval or the real line into subintervals, we need to bear in mind that we need the expected number of cases to be at least equal to 5 in each of the categories. If this doesn't hold, we need to merge the categories somehow so that this is followed, so that this is observed. Now, let's take a look at a simple exercise which looks like this. Here we go. A random number generator has generated 20 values which look like that, and we want to test whether the data come from the uniform distribution on interval 0, 1. Okay, so exercise 6.1. We measured n being 20, well, pieces of data, 0.055, 0.068, and so on, up to 0.932. And we want to test whether the data comes from the uniform distribution, uniform on the interval 0, 1. Okay, now you recall from the beginning of this course that the uniform distribution is such which has a constant density on the interval which is in question here, 0, 1. And in this interval, we have just observed the values being here, 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 there. And we want to ask whether they are uniformly distributed, and we want to use that approach, meaning slicing the interval into some subintervals, finding out how many points are in each of those subintervals, finding how many of them there should be on average, and comparing it using the chi-square statistic. Now, here we have 20 values, and if we want to divide this interval into some number of subintervals so that there will be the expected number would be at least 5. Now we can take a look at the interval and slice it into 4 pieces maybe. That would make sense, right? So we just slice the interval like this. Here we have 1/4, here we have 1/2, here we have 3/4. So we slice the interval into I1, which is from 0 to 0.25, I2, which is from 0.25 to 0.5, I3, 0.5 up to 0.75, and I4 goes from 0.75 up to 1. Good. So then we take a look how many observed values are in which of the intervals. So let's take a look. How many data points are in the first interval? 1, 2, 7, 8, right? If I take a look at it, then we have 1, 2, 3, 4, 5, 6, 7, 8 up to 0, 2, 0, 3, and then we have 1, 2, 3, 4, 5, 6, 7, 8 in the next bracket. One, 2, 3 in the last, and in the next, and 1 in the last. Okay. Now, those are the observed counts, right? Now, what are the probabilities of the individual brackets?
8 out of 20.
Sorry?
So for each category?
For each category was the probability under the null hypothesis of uniformity that a value falls in that.
So wouldn't it be like 8 out of 20, 8 out of 20, 3 out of 20, and 1 out of 20?
This is the observed. Careful about that. Those are the observed counts. We want to compare them with the expected counts under the null hypothesis of uniformity. So, under the null hypothesis of uniformity,
so 1/4 for everything?
we should have 1/4 of observations in the first one, okay. 1/4 in the second one, 1/4 in the third, and 1/4 in the last. Okay, so those are observed counts. Expected probabilities and the expected counts are just n times pi. So we just take 20 times 1/4, giving us
2. No, wait. Yeah, to write n times 1/4, so 8 times 1/4.
okay. N is how many observations we have.
Oh, so 20.
Now, thinking about it in the clear way, we have 20 observations, right? 20 data points. And under the hypothesis of uniformity, how many of them should be in each of the bins? 5, right? So this is like 20 times 1/4, which is 5, 5, 5, 5, right? We can visualize it on the interval, and okay, so we have from 0 to 1. Here we have the individual brackets, and here we have 8 observations. Here we have 8 observations, 3 observations, and 1 observation. And we are comparing this with the expected number of observations under the null hypothesis. Okay? And we are basically, by using the chi-square statistic, we want to say whether this deviation from the uniformity is okay enough to say that this data, well, might come from the uniform distribution, but it is within some statistical level of deviance, not being a problem, or whether this discrepancy actually shows that the data does not follow the uniform distribution. Okay? And well, how to evaluate that? Whether this is far enough or not, we use the chi-square statistic. Sum over all fields n I minus n times pi squared over n times pi. So this is 8 minus 5 squared over 5 plus 8 minus 5 squared over 5 plus 3 minus 5 squared over 5 plus 1 minus 5 squared over 5. This gives us 8 minus 5. This is 3 squared plus 3 squared plus 2 squared plus 4 squared over 5 being, well, 9 plus 9, that's 18, plus 4, that's 22, plus 16, that's 38 over 5. Do I have it correct? Yeah. Which is 7.6. And for level of significance alpha being 5%, we have the chi critical value alpha with k minus 1 degrees of freedom being chi 0.05 on 3 degrees of freedom. We take a look into the tables. 3 degrees of freedom for the chi-square is here, third row, and the critical value for 0.05 is 7.815. So we are in this situation. Here we have the critical region. Here we have the OK region. Here we have the bound 7.815. And here we have the chi-square statistic 7.6. Okay, so what do we do with the null hypothesis of uniformity?
We do not reject.
We do not reject. Okay, we do not reject the null hypothesis on level 5%. And by the way, the null hypothesis is that the probabilities are equal to 1/4 for all i's. And the alternative hypothesis is there exists such an I for which the probability is not equal to 1/4. Okay? Now, does it make sense?
Yep.
We are comparing the observed number of observations in each of the brackets to the expected number of observations. Okay, now if we would like to do this test in a computer, we could. I have written a small script which you can run yourselves. Okay, here I have initialized the vector. I have set the number of bins, and what did I do is I multiplied the x's with the numbers of bins to scale it from 0 to 1 to 0 to 4, and then applied the upper part. So I just got the indicators of the individual observations falling in the respective brackets. Then I apply the table function, which gives me the expected, the observed counts, and when I found the expected counts, I found the, n is what? Oh, n is the table. Good. So that's the chi-square statistic, which is exactly 7.5. And if I would like to find p-value, I could look in the tables. Here I have 7.6, the critical value. So I know that 7.6 on 3 degrees of freedom is between 6.25 and 7.815, meaning that the p-value of that test is somewhere between between 5% and 10%. And if I would like to find the critical value exactly, what I could do is either find it using the inverse of the critical value, which is the, well, in this case, the p chi-square function in R. It has similar call in Python. Or what I could do is simply take the table of the individual individual counts and just insert it into the function chi-square dot test. And this function takes the table of the observed counts and performs exactly the test of uniformity, giving me the chi-square statistic and the p-value of the test. Okay, and because the p-value is larger than 5%, we do not reject the null hypothesis on level of significance 5%. Okay, so chi-square test on the n's. Yeah, that's like the vector n1 up to nk. And if I would like to test for a different distribution than uniform, I will here just need to specify the vector of probabilities by giving p being equal to a vector of given probabilities. If you ever need this, you can find the documentation for that function yourself if you encounter this in practice. Okay? Does it make sense?
Yeah.
Now, that's one of the application of the chi-square tests. There is another one which goes one step forward and instead of a one-dimensional distribution takes into account a two-dimensional distribution. And wants us to test whether the two dimensions are actually independent or not. Now, you can imagine that you can ask, for example, 100 people whether they are right-handed or left-handed. That's one category. And then you can ask them whether they have dark hair or light hair. That's another category. You get a table of numbers of observations. Yeah, you have this and this many people in that category, in that category, in that category. And based on this table, you might want to test, verify whether the categories are independent or not. Yeah, whether it does not depend whether the person is right-handed or left-handed on the color of his hair. Now, this actually, if we think about that, and if we think about a two-dimensional discrete distribution being just an ordered extension of a one-dimensional distribution, we can find out that this test is actually pretty simply done by using the chi-square test, chi-square goodness of fit test. So, and this procedure is called testing independence in contingency tables. Okay, so let X be a two-dimensional vector YZ with Y having possible values 1 to R and Z having values 1 to C. Why R and C? Because by this we mean the rows and columns. And let Pij mean the probability that Y is I and at the same time Z is J. And then we have the joint probabilities given in a table where we have for Y we have possible values 1 to R, for Z we have possible values 1 to C, and here we have like Pij, the individual probabilities. Now, if we think about what we know about random vectors, immediately can say that we immediately can find the marginal distributions of each of the variables, right? If we have Y being the individual rows and we take row sums, we get the marginal distribution for Y. And the same way, if we take column sums, we get the marginal distribution for Z. So, and in this case, we denote them with a bullet. We take the notation using the small p for probabilities, and by taking the sum over one coordinate, we denote that by using a bullet in that coordinate. Okay, so here we have like P1 bullet, P2 bullet up to PR bullet, and here and here we have P bullet 1, P bullet 2 up to P bullet C. And now you recall that two random variables, which are discrete, are independent. Now, when they are independent, recall?
When one doesn't affect, when knowing about the result of one doesn't affect how much you know about the other one, right?
Yes. Now, this is what it means, generally speaking, and mathematically, how would you verify it?
Try to calculate one of the elements of probability of one of those groups and calculate it again when like we decide a result in another group. I
know. I think I know what you mean. Comparing the conditional distribution of one variable under the given value of the other, and see whether this conditional distribution is the same for, let's say, z being this, z being this, z being this. Okay, this would work. But if we'd like to, well, algorithmically find out whether y and z are independent, there is one simple condition which we want to verify.
The joint density equals the product of marginal densities?
That's for continuous, and for discrete, instead of densities, we have just the probabilities, okay? So, y and z are independent whenever, for all i's and j's, the joint probabilities are equal to the product of the marginals, in this case pi bullet times p bullet j. Okay? And now this is a hypothesis concerning the parameters of this distribution. So this is our null hypothesis, which we want to test against the alternative that there exists some field where this doesn't hold. There exists a combination ij so that the probabilities do not match. Okay, now how can we do that? First, let us observe a sample from this distribution, meaning let us ask some number of people what's their hair color and whether they are left or right-handed, or any other categories which we might want to investigate. Basically, let's perform a random sample. So we take a sample of n observations. Let's see, x, y, and let n I j denote the number of observed cases in each category. Okay? And by putting the observed numbers of cases in a table, we get the so-called contingency table. Now, just the number of cases in each of the category. Yeah? A contingency table, y, z, just shows us the number of cases which are observed in each of the categories, N1C, NR1, and in the middle there are just the observed numbers of each of the categories. Now, by taking row sums and column sums of this table, we get just the numbers of individual categories separately for one of the variables and for the other. So here we take row sums and column sums representing the number of cases in each of the marginal categories. And altogether, the number of cases needs to be equal to n. And then what we do is we estimate the probabilities, marginal probabilities, by taking the individual, row sums and individual sums of observed counts and dividing them by n. So we estimate Pi bullet using Ni bullet over n and P bullet j using n bullet j over n. Those are estimated marginal probabilities. If we multiply them, we get the ideal probabilities under the hypothesis of independence. And if we multiply them back again by n, we get the expected number of cases in each of the category under the null hypothesis of independence. So, by taking, this is like Pi with a hat, and this is P let j with a hat. And by taking n times P I bullet with a hat times P bullet j with a hat, we get the expected number of cases in each category under the null hypothesis of independence. Now, what does it mean practically? Now, it means that we have the observed counts and we have the expected counts under the hypothesis which we want to investigate. So we can compare them using the chi-square statistic. The same way as we did before, but here we are just going over the all individual rows and columns of the contingency table. Not this. And for testing, we use the chi-square statistic, which is just sum over all rows, sum over all columns, Nij minus n times p hat I bullet p hat bullet j squared over n times pi bullet times p bullet j. Okay, and this statistic has a chi-square distribution and we need just to be careful about the number of degrees of freedom in this case. Now you recall that when we were testing goodness of fit, when having a distribution with some parameters, we needed to estimate the parameters by using the minimal chi-square method, which is a bit difficult to do on paper. It can be done using a computer, and then we need to subtract the number of parameters of the distribution from the number of degrees of freedom. And now, if you think about the parameters which we are estimating, and how many are there? We are estimating the marginal probabilities, okay, like P1, Pi1, Pi2, and so on and so on. So for each row, we are estimating the marginal probability for variable x, for variable y, and for each column, we are estimating the marginal probability for variable z. And this would mean that here we have r parameters to estimate, and here we have c parameters to estimate. But when taking into account that they add up to 1, they are not all three. They are bound to be altogether equal to 1, meaning that if we estimate every one but the last then needs to be equal to 1 minus the sum of the last of them. So we do not have r parameters to estimate here, but only r minus 1, because the last of them can be computed out of them. So here r minus 1 parameters, and here c minus 1 parameters to estimate. And with the number of degrees of freedom is k minus m minus 1. This is the number of categories, and this is the number of parameters. And now if we take a look at the table, then we have r times c categories. And number of parameters is r minus 1 and c minus 1. So we have r times c minus r minus 1 plus c minus 1 minus 1, altogether r times c minus r minus 1 minus c, minus plus 1 minus 1, these ones get cancelled. And we have r times c minus r plus 1 minus c And then we can think about this R times C minus R being R times C minus 1. And this plus 1 minus C is like minus C minus 1. And if we put C minus 1 out, we get C minus 1 times R minus 1, altogether R minus 1 times C minus 1 degrees of freedom. So, when we want to test whether some categories are independent based on a sample of given size, what we do is out of the observed counts in each of the categories, we find the marginal sums by taking just row sums and column sums. We divide them by n to get estimated probabilities, or marginal probabilities. Then we multiply the marginal probabilities together to get, well, product of marginal probabilities being the joint probability under the null hypothesis of independence. We multiply them back by n to get expected number of cases in each category under the hypothesis of independence, and then we compare the observed and expected counts using the chi-square distribution. And if this chi-square statistic exceeds the corresponding critical value of the chi-square distribution with R minus 1 times C minus 1 degrees of freedom, we just reject the null hypothesis of independence. Okay? Now the chi-square statistic can be rewritten by playing with the n and with the estimated probabilities, but I find it easiest to remember that we are just comparing the observed counts with the expected counts under the null hypothesis. Now, does it make sense, at least from the intention, what we want to do? Good. So let's try doing this on an exercise. Now, before we go forward, we need at least 5 observations, so expected observations. In each category. If this doesn't hold, then the procedure doesn't produce reasonable results, and to avoid this, we might need to merge some categories, some columns or rows. We will see exactly how this works. Now, let's take a look at exercise 6.3, I guess. Yeah. Oh no. Yeah. Here we go. 6.2 is it is. Suppose we want, well, there is a company which runs 4 call centers, and the company wants to find out whether the customers are satisfied or not satisfied by being routed into this or that call center, and the company wants to find out whether the fact that the customer was satisfied was actually dependent on to which call center was he routed. Yeah, this makes sense. They have one call center in this city, one call center in that one. They operate independently. They are different people. They might have different hiring procedures, whatever. And the helpline is operated automatically, and the calls are routed randomly to just the place which is free at that point. So it is a valid concern whether all of those call centers are operating, or the satisfaction is the same, or whether it is not. So 6.2, we have 4 call centers, and being 100 callers. And we have the observed counts of individual categories as follows: satisfied, not satisfied, and we have center 1, center 2, center 3, center 4. In center 1, that was probably pretty new because there was just one customer who was satisfied and no non-satisfied customers. So during this study, center was almost not in it. In the second center, 11 satisfied customers, 8 not satisfied. In the third center, 7 satisfied, 23 not. Doesn't seem that good. And in the fourth, 21 and 29. And we want to test on level alpha is 5%, whether the satisfaction of customers and assigned call center are independent. Okay, so those are our observed counts N, I, J. So first, we need the marginal counts N, I, bullet. Okay. So we take just the row sums and take a look, and the column sums and take a look. Here we have like an I bullet, and here we have like an bullet J. 1 plus 11, that's 12, plus 7, that's 19, plus 21, that's 40, and here we have O plus 8, it's 8, yeah, and altogether 23 plus 8 makes 39, plus 29 makes 60. Okay, so out of the callers, altogether in the study, 40 were satisfied and 60 were not satisfied. Okay? So, and out of all of them, 1 was routed to center 1, 19 were routed to center 2, 30 were routed to center 3, and 50 were routed to center 4. Now, if you want to check whether you haven't made a mistake, you can see whether the counts altogether add up to 100 in each of the dimensions. Here it is plain. Here we have 1 plus 19, that's 20, plus 30, 50, plus 50. It holds. Okay, so that was the first step. Then we estimate the marginal probabilities. Yeah, the marginal probabilities, as we have seen, are just P with the head, I bullet, which are just N I bullet over M, and P bullet J, which is N bullet J over N. So we just take the numbers which we have there on the edges and divide them by 100. So here we have 1 over 100, which is 0.01, then 0.19, 0.3, 0.5, 0.4, 0.6. Okay. That was the next step. And now, under the null hypothesis of independence, the probabilities of the individual fields should be the products of the marginals, right? So we estimate or just calculate the expected probabilities of categories under the null hypothesis. Yeah, the Pij is then Pi bullet hat times P bullet I hat. So we just take the marginals, multiply them all together, and get the ideal estimations of probabilities under the null hypothesis of independence. So here we have 0.004, 0.006, and now 19 times 4, that's 38, times 2, 60, 75, 0.76. Here 0.3 times 0.4, that's 0.12, 0.5 times 0.6, that's 0.3. Yeah, here we have, right? I bullet, P bullet J. Inside 6 times, 5 times 0. Here we have 0.2, 0.6 times 0.5, that's 0.3. 0.3 times 0.6, that's 0.18. And here, 0.6 times 0.19, I just need to take a look here. Yeah, 0.114. So those are the ideal probabilities under the null hypothesis of independence. And now we need to convert them into the expected number of cases under the null hypothesis. So we just take the probabilities and multiply them by the number of observations. So by 100, which is simple, just switching the decimal by 2 points. Okay, so we estimate or calculate the expected number of observations in each category. Okay, so let's take a look. N times P I bullet times P bullet J just makes us take those numbers and multiply by 100, giving us 0.4, giving us 0.6, giving us 7.6, here giving us 11.4, here giving us 12, here giving us 18, here giving us 20, and here giving us 30. So those are the expected numbers of callers which would fall into each of the categories if the satisfaction would to be independent on the assignment of the call center. Okay, now before we calculate the test statistic by taking just the expected numbers comparing, the observed numbers, comparing them with the expected numbers, we need to be careful about the condition that we have at least 5 in each category. We do not. Here it's less than 1, so it wouldn't work. But it is designed so that if we merge these two categories together, yeah, this is satisfied and not, and this is call center 1, call center 2, call center 3, call center 4. And if we would merge these two categories together, we would get pretty reasonable numbers, right? So we need at least n times Pi bullet times P bullet J being equal to 5 in each category. This doesn't work here. We need to merge the categories together. And we take those we need to merge C1 with one of the others, and it's most simple to merge it with C2. So we get a simplified table giving us 8 here, 12 here, 12, 18, and 20, and 30. And we compare this the observed counts Nij with the merged categories C12, C3, C4, satisfied and not satisfied. So here we merge 1 with 11, so we get 12. Here where we merge 0 with 8, we get 8, and this is what we just copied. 7, 23, 21, 29. Okay, so those are the expected counts under the null hypothesis. You see that those are proportional. The number of not satisfied customers is in each of the categories half that larger than the number of not satisfied is half that larger than the number of satisfied. This is the proportionality given by the independence condition. Okay, and now we are comparing whether the actual observed counts are sufficiently close to the expected ones to say that, okay, variables are independent, or whether they are far enough to say that they are not. So then, the chi-square statistic is just the sum over all rows, sum over all columns, Nij minus n times p I bullet p bullet j squared over the expected counts. So, what do we have? 12 minus 8 squared over 8 plus, and I will just go field by field. So then I have 8 minus 12 over 12 plus 12 minus, oh sorry, 7 minus 12 over 12 squared plus 23 minus 18 squared over 18 plus 21 minus 20 squared over 20 plus 29 minus 30 squared over 30. Okay, and now we just compute this. Here we have 4 squared over 8 plus 4 squared over 12 plus 5 squared over 12 plus 23 minus 18, 5 squared over 18 plus 1 squared over 20 plus 1 squared over 30, and when having a calculator we can simply find out that this is 6.88. And the chi-square statistic is then compared with the critical value with R minus 1, C minus 1 degrees of freedom. And here we have R minus 1 is 2 minus 1 times 3 when taking into account the merged version, 3 minus 1, so this is like 1 times 2, which is 2. So 2 degrees of freedom. So we take a look at the tables. Oh, sorry. 2 degrees of freedom, 0.05, giving us 5.991. So here we have the chi-square distribution, there the critical region, 5%, 95% the OK region. Here is 5.991, and here is the test statistic, 6.88. And what does it mean about the null hypothesis?
We reject it.
We reject it. Okay? All no of significance. 5% in favor of the alternative that the variables are not independent. Practically speaking, this means that the various call centers have different satisfaction rate among the customers, and they have a statistically significant different satisfaction rate. Okay? Now, if you decide to do the homework, you would be asked to compare two texts, and by using this approach, compare whether the distribution of letters in the two texts is the same or whether it is not. You would get randomly assigned two texts out of a pool of 20. Some of them come from older books, some of them come from newer books. So you might hypothesize that they would actually use different structure of words, different structure of letters. So you can verify this exactly by the same means, just taking book 1, book 2, and A, B, C, D, and so on and so on. You only need to be careful about the condition on expecting at least 5 letters in each of the categories. You will see that some of the letters like Z and Q or J even are not that often used. This is what you find out when you try that. Does it make sense?
Yes.
You can take a look in the in the lecture slides, there is one more exercise which compares to Eastern Bohemian regions and compares how many kids does a mother have, 1, 2, or 3 and more, and tests whether there is a significant difference among the two regions, and finds out even that there is. Well, you can try working that out yourselves. Now, as an aside note, before we move forward, there is quite a large scale of problems for which we can design a test. Now, at most of the cases, a test is designed by establishing a testing statistic which compares the observed behavior with the expected behavior under the null hypothesis. You have seen that on the one sample t-tests when we were comparing the average of some observations with the expectation given by the null hypothesis. We are comparing the average volume of beer with the expected volume of beer under the null hypothesis of that they are not cheating on us. Here we were using a different approach. We were comparing the counts of some categories in a table which we observed to the expected number of counts which should be in the table given that they are independent. Now, the American National Institute of Standards and Technology, abbreviated as NIST, is doing similar testing on random number generators. Testing by assessing their different facets on whether they produce actually random numbers. Now, what do you understand under the word random? What should the test be? What should the generator be? What the values generated using the generator should follow? What should hold? That it would be actually random.
And a uniform distribution.
This is one of the options. One of the options which we might want to simulate. It's the most common, simulating from a uniform distribution. Yes, but there's even one more property which signifies what it means that something is actually random. Suppose you are simulating a sequence of numbers. Yeah, you start running a random generator and you just are running some algorithm which, well, gives you numbers which try to be as close to random as possible. Now, what would you want from the numbers?
Something to do with entropy, maybe?
Yes. One of those tests is based on the entropy, but this is tied to the distribution. Any ideas? Now, suppose I'm generating a sequence.
It should not follow like a normal distribution. All the numbers should have the same opportunity of appearing.
This means that they should have a uniform distribution. Like, okay, but this all takes into account just the observed value. The critical thing on such random number generators is that they should be unpredictable. Meaning that if you have a sequence of numbers, then given the sequence, you shouldn't be able to predict what comes next. Okay? So the next value of the generator should be looking like if it was independent on the ones which came before it. Now, this is pretty hard to do when you have just a computer at your disposal, right? Because you can just write an algorithm which is pretty much deterministic. If you just doesn't plug in a physical device as in a cloud counter or a humidity counter or some temperature counter, something which is inherently random by a physical nature, if you do not plug in such a device in your computer, you would always get an algorithm which is in some way deterministic. And those deterministic algorithms just want to look like they are producing numbers which you can't guess. But if you would know what are the parameters of the programs, you would be able to do less. Most of the generators are just multiplying some prime numbers with each other, then adding a bit, then taking a modulo with respect to another prime number, just to fake the independence for a human being not being able to determine it. And when somebody comes with a new random number generator computer programmed on a computer, there is a battery of tests which the Americans use before it can be used in practice, for example, in security algorithms and so on. Yeah, there are quite a lot of those tests, and the algorithm needs to pass them all. And we'll just take a look at two of them. Yeah, here at the time of the writing of these slides, there were 15 basic tests, which some other subtests, which focus on, well, the quality of the random generated data. And the ones which I want to show you are such, which focus on the independence of the individual variables. Now, if you take values from some distribution, by taking a look at the sequence which you have in front of you, you shouldn't be able to guess what comes next. Now, it can be shown that if a sequence is truly independent, and it comes from a distribution which oscillates around some expectation, then you should have some numbers above the expectation and some numbers below the expectation. That's one thing. The other thing is, if you take a look at sequences of blocks which are either above the expectation and below the expectation, they shouldn't be too long and they shouldn't be too short. Now, if you would have a generator which generates 50 numbers above the expectation and then generates 50 numbers below the expectation, that's a wrong one, because if you observe one number, there is a larger probability that the next one will be on the same side of the expectation than that it would be on the other one, right? That's wrong. Another thing is, if the generator would proceed in a different way, if it would generate values above, below, above, below, above, below, above, below, that's also wrong, because if you get a value which would be here, then you know that the next value is much more likely to be on the opposite side than on the same one. So, people wanted to find out what is the optimal length of blocks being above and below. And even they were able to find out under some specific circumstances, when the distribution which we are talking about is symmetric around its expectation and the expectation is equal to the median and no value can be equal to the expectation, that the number of blocks which run above and which run below and not cross the expectation has, for true independent sequences, the number of blocks which do not cross the expectation for large n has a normal distribution with expectation n plus 1/2 and variance n minus 1/4. That's a pretty hard thing to imagine, but the number of blocks which do not cross the expectation is just a sum of some indicator variables, 0, 1 variables having some properties. And whenever you see a sum of some variables, you might think that there is the central limit theorem in play, which forces the sum at the end behave approximately like a normal distribution. So this is not easy to prove, but it can be used to compare the number of blocks above and below the expectation with the expected number of them under the hypothesis of independence, and find out whether the number of blocks running above and below the expectation is actually sufficiently close to this for the generator not to be this predictable or this reversely predictable. Okay? Okay, so now we make a break, and after that we'll see an exercise where this would make sense.
Can you lower the...
Oh, yes, sorry. Good. Okay, so we'll continue in 15 minutes.
Okay. Wanna go get some air?
Let's go.